હવે જો આપણે ફોટો ઇલેક્ટ્રિક ઇફેક્ટ ડિસ્કસ કરી. In that we studied this thing. In photoelectric effect, we can observe this thing when the radiation or the light with sufficient frequency incident on the metallic surface, then the electrons are emitted from the surface. And experimentally, we observed this thing. The number of electrons emitted from the surface that depends on the intensity of the incident radiation. Means that photoelectric current that depends on the intensity of the radiation and the maximum kinetic energy with which electrons are emitted, that depends on the frequency. And this particular phenomenon, that is instantaneous one, means as soon as the radiation, or we can say light incident, within the time interval of nanosecond, the electrons are emitted. And here the radiation, that must be with some minimum frequency. So the frequency that is called threshold frequency, if the incident radiation have the frequency less than this threshold frequency,
Sir, full screen कर लो.
then the radiation will not be, that will not be able to emit the electrons. Okay. So if the frequency of the incident radiation is less than that minimum value of the frequency, which is called threshold frequency, then the photoelectric effect is not observed. આવું બધું આપણે experimental study કર્યા. Okay. લેનાર્ડ અને હોલવાર્સના experimental observations છે, આપણે આ બધા conclusions લઈ આવ્યા. Okay. Then after, when they tried to explain this particular phenomenon with the help of the established fact, the light have wave nature. So by considering this fact, when scientists tried to explain this particular phenomena, then they totally failed. It implies that wave nature of light totally failed to explain this particular phenomenon, photoelectric effect. Okay. Then after scientist Einstein gave the explanation for this photoelectric effect. Actually, before that, the concept related to the quanta of energy was represented by Planck. Planck suggested this thing when he studied about, or when he tried to give the explanation about the black body radiations. So he suggested this thing, the radiation emitted, or we can say the energy emitted in black body radiation process, that is in the form of quanta of energy. And the minimum quanta of energy, that is equal to hf, or we can say h nu, where h is Planck constant and nu, that is the frequency of the radiation. So radiation is made by different quantas of energy. Means radiation possesses the energy in the integer multiple of hf. And this particular quanta of energy, that is known as photons. Known as photon. So continuous emission of the energy is not there. Energy is emitted in the form of quanta, hf, 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 like that, or 2hf or 3hf. So it is always in the integer multiple of hf. So energy that is emitted equal to nhf, where n, that is integer, 1, 2, 3, 4, like that. But he suggested this thing, energy is emitted in the form of quanta, and then after it propagate in the form of wave. But actually, this one was controversial because classical mechanics says this thing, if we consider any oscillator, then it can possess any energy from maximum to minimum. And here, the quanta of energy, that is against the classical mechanics. એટલે એ થોડું કન્ફ્યુઝિંગ થઈ ગયું હતું એ વખતે. પણ પછી એ જ કોન્સેપ્ટને આઇન્સ્ટાઈને થોડો આગળ ડેવલપ કર્યો. આઇન્સ્ટાઈને ત્યાં સુધી કીધું કે light means radiation incident in the form of quanta, it interact with the electrons in the form of quanta, and the emission that is also in the form of quanta. Okay, તો આ રીતનું આખું એણે એક્સપ્લેનેશન આપ્યું. હવે એણે જે એક્સપ્લેનેશન આપ્યું એનાથી ફોટો ઇલેક્ટ્રિક ઇફેક્ટ કેવી રીતે પરફેક્ટલી એક્સપ્લેન થઈ. ઓકે, so he suggested this thing, when the radiation which possesses the quanta of energy, that is h nu, or we can say hf, where h that is the Planck constant and nu or f that is frequency of the radiation. Okay, so when that particular quanta of energy incident on the metallic surface and interact with the electron, so if this particular energy is greater than the work function of the metal, then electron will be emitted, otherwise not. Okay, now see, if this particular energy is greater than work function of the metal, then electron will absorb this entire one. Very first thing, એમાં એવું નહીં કે એમાં પાર્ટલી એબ્સોર્બ કરે કે એવું નહીં, આમાં બે જ વસ્તુની પોસિબિલિટી, રેડિયેશન એટલે કે ક્વોન્ટા ઓફ એનર્જી ઇન્સિડેન્ટ થયું, આઈધર ઇટ વિલ બી એબ્સોર્બ્ડ ઓર રિફ્લેક્ટેડ. જો રિફ્લેક્ટ થઈ ગયું તો પછી એની સાથે કોઈ લેવા દેવા નથી આપણે, એબ્સોર્બ્ડ તો પછી એન્ટાયરલી એબ્સોર્બ્ડ. બરોબર છે? તો હવે h nu energy of the quanta is greater than the work function of the metal, then the energy equal to work function of the metal that will be utilized to be free from the metal. અને જો exactly work function જેટલી જ એનર્જી વાળું રેડિયેશન ઇન્સિડેન્ટ થયું હોય અને એ એબ્સોર્બ થઈ જાય તો ઇલેક્ટ્રોન ફ્રી થઈ ગયો મેટલથી, but now we can say it is with zero kinetic energy. પણ જો વર્ક ફંક્શન થી વધારે એનર્જી એબ્સોર્બ થઈ તો વર્ક ફંક્શન જેટલી એનર્જી ફ્રી થવામાં યુટિલાઇઝ થાય, and rest part of the energy that will be possessed by electron in the form of kinetic energy. So we can say this thing, when h nu is greater than 50, then electron will be emitted with maximum kinetic energy, that is h nu minus 50. And this particular equation, that is called Einstein's photoelectric equation. Okay, now see, here we can observe this thing, the maximum kinetic energy that linearly depends on the frequency of the incident radiation, and it is independent of the intensity of the radiation. So this one is in perfect agreement with the observations. Clear? And here we can observe this thing, if the frequency of the incident radiation is less than a particular frequency, that is the threshold frequency nu 0, that is 50 by h. Because 50, that is the work function. Work function means the minimum required energy to make electron free. So energy, that is h into frequency. Okay. So minimum required energy, that is associated with the minimum frequency, and that is threshold frequency. So we can write nu zero, that is 50 by h. Okay. Now see here, we already discussed this thing, K maximum, that is equal to EV0. So we can write EV0, that is h nu minus 50, where nu is greater than nu zero. So we can write V0, the stopping potential, that is h by E into nu minus 50 upon E. So if we draw the graph of stopping potential versus frequency, then that will be the straight line, and slope of it, that will be h upon E. And this one is also in perfect agreement with the observations. Then after, if we think about the intensity, see what is the definition of intensity? So amount of energy incidenting on the surface per unit area per unit time normal to it, that is called the intensity of the radiation. Okay. હવે intensity અને photoelectric current એ બે એકબીજા સાથે એસોસિએટ છે, આપણે ડિસ્કસ કર્યું. If intensity is more, the photoelectric current is more, એટલે કે number of electrons emitted will be more. તો હવે જો એનું એગ્રીમેન્ટ અહીંયા પરફેક્ટ કેવી રીતે આવે છે? Now radiation, it is made by quanta of energy. હવે જો radiation સપોઝ કે બે ક્વોન્ટાનું બનેલું હોય તો 2hf એનર્જી ઇન્સિડેન્ટ થાય, રાઈટ? તો માનો કે ઇલેક્ટ્રોનને hf જેટલી અથવા તો h ન્યુ જેટલી એનર્જી એક ઇલેક્ટ્રોન એબ્સોર્બ કરે છે. તો રેડિયેશન તમારું બે ક્વોન્ટાનું બનેલું હોય તો બે ઇલેક્ટ્રોન એબ્સોર્બ કરશે અને બે ઇલેક્ટ્રોન એમિટ થશે. If your radiation is made by 5 quanta of energy, each one is with energy h nu, તો પછી 5 ઇલેક્ટ્રોન એને એબ્સોર્બ કરશે અને 5 ઇલેક્ટ્રોન એમિટ થશે. It implies that if the number of photons, or we can say number of quanta of energies, increases on the incident surface, then we can say its intensity increases because amount of energy incidenting increases. And corresponding to that, more number of electrons will be emitted. So the dependence of the number of electrons emitted from the surface on the intensity, that can be perfectly explained with the help of this equation also. So finally, it was established, Einstein's explanation was perfect one, and it was accepted there is the duality in the nature, and in some favorable conditions, wave behave as a particle. And this particular particle nature of the wave, that is known as photon. So this quanta of energy, that is known as photon. Clear? And this quantization also proved by Millikan experimentally. Okay. So quantization exists in the nature. Clear to all of you, or any doubt in this one? So particle nature of light, that is called photon. So now we have to think about some characteristics of photon. Okay. So Einstein arrived at the important result that the light quantum can also be associated with momentum, and that momentum is given by h nu by c. It implies that when light behaves as a particle, then we know this thing. If particle is there, then definitely it must have some momentum. Okay. And that momentum is given by h nu by c. Okay. Now, definite value of energy as well as momentum is a strong sign that the light quantum can be associated with the particle. Okay, and it was named as photon. Okay, then in interaction of radiation with matter, that radiation behave as if it is made up of particles called photon. Second thing, each photon has energy equal to h nu and momentum, that is h nu by c, where c, that is the speed of light. Then all photons of light of particular frequency nu or wavelength lambda have the same energy. Okay, and that energy, that is h nu or hc by lambda, and momentum, that is h nu by c or h by lambda, whatever is the intensity of the radiation, but the energy of all the photons, that will be same one. Okay, now by increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area. So automatically the energy crossing the given area will increase, because with each photon the energy associated, that is h nu. So if number of photons increases, then energy also increases. Thus photon energy is independent of the incident intensity of the radiation. Then photons are electrically neutral and are not deflected by the electric and magnetic field. In a photon particle collision, the total energy and total momentum are conserved, because when we consider the radiation as a particle, then in standard 11th we already studied this thing, when there is the interaction between the particles, the total energy and total momentum, that will be always conserved. So in the case of photon also, the interaction between photon and with any other particle, the energy and momentum will be conserved. It implies that law of conservation of energy and law of conservation of momentum, that will be obeyed. Clear to all of you? So these are the characteristics of the photon, means the particle nature of the photon. Example 11.1. Monochromatic light of frequency 6 into 10 raised to 14 Hertz is produced by a laser. The power emitted is 2 into 10 raised to minus 3 watt. What is the energy of a photon in the light beam? B. How many photons per second on an average are emitted by the source? Now see, each photon, that is with energy equal to h nu, h, that is Planck constant 6.63 into 10 raised to minus 34 joule second, and the frequency given to you, that is 6 into 10 raised to 14 hertz. So you will get the energy of the photon in the light beam, that is 3.98 into 10 raised to minus 19. અને સોલ્વ કરશો એટલે આન્સર આવશે, આપણે ડાયરેક્ટ લખ્યો છે. Now suppose this particular radiation is made by n number of photons. Okay, so if n is the number of photons emitted by the source per second, it implies that the power P transmitted in the beam equals n times the energy per photon, because energy per unit time itself is called power. Okay, so we can write now power, that is n into E. upon time લખવાની જરૂર નથી, કારણ કે 1 second આપણે already લીધેલું છે. So number of photons, that is P by E. Okay, so the total power emitted, that is 2 into 10 raised to minus 3 watt, divided by the energy of each photon, that we calculated here, 3.98 into 10 raised to minus 19 joule. Then here solve this one, that much number of photons are emitted per second by the source. Clear to all of you? Any doubt in this one? Example 11.2. The work function of the cesium is 2.14 electron volt. Find A, the threshold frequency of cesium, and B, the wavelength of the incident light if the photocurrent is brought to zero by the stopping potential of 0.6 volt. Now see, the work function, that is 2.14 electron volts, so 2.14 into 1.6 into 10 raised to minus 19 joule. Threshold frequency. Now we have the equation 50, that is HF0. So F0, that is 50 upon H. 50 in joule, that is 2.14 into 1.6 into 10 raised to minus 19 upon H, that is 6.63 into 10 raised to minus 34. Solve this one, you will get the threshold frequency. Now stopping potential given to you, that is 0.6 volt, lambda, that we want to calculate. Now we have the equation as per Einstein's photoelectric equation. We can write EV0, that is HF minus 50. F, the frequency, that is C by lambda. So that is Hc by lambda minus 50. So we can write EV0 plus 50, that is Hc by lambda. So lambda equal to Hc upon EV0 plus 50. Okay. Now this is equal to Hc upon EV0, 0.6 E as it is, and V0, that is 0.6 volt. So this will turns to 0.6 EV. And the work function given to you 2.14 EV. So resultantly you will get Sc upon 2.74 EV. Then H into C, that is 1.989 into 10 raised to minus 25. Divided by 2.74, multiply it by 1.6 into 10 raised to minus 19. So resultantly you will get lambda in meter. Clear to all of you? Any doubt in this one? Example 11.3. The wavelength of light in the visible region is about 390 nanometer. For violet color, about 550 nanometer. Average wavelength for yellow-green color, and about 760 nanometer for red color. A. What are the energies of photons in electron volt at the violet and average wavelength yellow-green color and red end of the visible spectrum? Take H equal to 6.63 into 10 raised to minus 34 joule second, and 1 electron volt, that is 1.6 into 10 raised to minus 19 joule. B. From which of the photosensitive materials with work function listed in the table, and using the results of 1, 2 and 3 of question A, can you build a photoelectric device that operates with visible light? Now, table for work functions of some metal given to you. Here the metals and the work functions. Okay. Now we have to check this thing with the help of which metal we can make our device photo, which give you photoelectric effect, or it is also known as photocell. Clear?
Sir, our table याद रखना.
Now see, for violet, lambda, that is 390 nanometer, so that is 390 into 10 raised to minus 9 meter. For yellow green, lambda Yg, that is 550 nanometer, that is 550 into 10 raised to minus 9 meter. For red, lambda R 760 nanometer, that is 760 into 10 raised to minus 9 meter. Now, the energy of all these wavelengths. So EV, that is Sc upon lambda V, that is 1.989 into 10 raised to minus 25 upon 390 into 10 raised to minus 9. When you will solve this one, you will get the energy in terms of joule. So then after divide it by 1.6 into 10 raised to minus 19, you will get energy in terms of electron volt. And your answer will be 3.19 electron volt. Then after energy of yellow green, Sc upon lambda yellow green, Sc that is 1.989 into 10 raised to minus 25 divided by 550 into 10 raised to minus 9. Again you will get in terms of joule, then divide it by 1.6 into 10 raised to minus 19. You will get answer in terms of electron volt, and your answer will be 2.26 electron volt. Then energy of red region, ER that is Sc upon lambda R, again Sc that is 1.989 10 raised to minus 25 divided by 760 into 10 raised to minus 9. Again you will get answer in joule, divide it by 1.6 into 10 raised to minus 19. You will get answer 1.64 electron volt. Now these are the energies associated with these radiations given to you. Now this one is the visible range of the light. So here see now, the work function for different metals are given to you. We have to use this visible light. Now we know this thing. If the energy of the incident radiation is greater than the work function of the metal, then and then only the photoelectric effect is possible, otherwise not. Now see here, the energy associated with violet, that is 3.19, for yellow green 2.26, and for red 1.64. Now the photoelectric device will operate with violet light with energy 3.19 electron volt of photosensitive material Na, because work function of Na that is 2.75 electron volt, and K potassium with 502.3 and cesium with 502.14 electron volt. Clear? બાકી આ બંને જે છે એની જે એનર્જી છે એ તમે જુઓ 2.26 અને 1.64. તો 2.26 થી તમે cesium થી ફોટોસેન્સિટિવ સરફેસ બનાવી શકો, બરોબર છે, અથવા તો ફોટો ઇલેક્ટ્રિક ઇફેક્ટ આપે એવી ડિવાઇસ તૈયાર કરી શકો. બાકી બીજી કોઈ મેટલથી તમે બનાવી શકો નહીં, કારણ કે દરેક મેટલનું વર્ક ફંક્શન જે છે પછી એ આપણે જે રેડિયેશન્સ લીધા એના કરતા વધારે છે. રાઈટ? ચાલો, ક્લિયર ટુ ઓલ ઓફ યુ?
Sir.
Then after, the Broglie hypothesis for wave nature of matter or particle. See, here one thing that we have to make clear in our mind, de Broglie suggested this thing in the form of hypothesis only, right? De Broglie suggested this thing, there is the symmetry in the nature. Always we observe a proper symmetry in the nature. So logically he thought like this: if wave have a particle nature, it implies that in certain circumstances when wave behave as a particle, then particle also behave as a wave in certain favorable circumstances, because there is the symmetry in the nature. એટલે કે જો વેવ ને પાર્ટિકલ નેચર છે તો પછી પાર્ટિકલ ને બી વેવ નેચર હોવો જોઈએ. અને એ એને કન્સિડર કરીને પછી હાઇપોથેસિસના ફોર્મમાં એને પાર્ટિકલનો વેવ નેચર represent કર્યો. Means when particle behave as a wave, then if its wavelength is lambda, then we can write lambda that is equal to h by p that is the momentum, so that is mv. So this particular wavelength of the particle when it behave as a wave, that is called the Broglie wavelength. That is called the Broglie wavelength. And when the particle behave as a wave, that particular wave, that is called matter wave. That is called matter wave. પણ આ બધું એને હાઇપોથેસિસના ફોર્મમાં રિપ્રેઝન્ટ કર્યું હતું. એટલે એક્સપેરિમેન્ટલ એવિડન્સીસ તો જોઈએ પછી આપણે, એના વગર તો થોડું એક્સેપ્ટ થાય વસ્તુ. ઓકે, નાઉ સી હિયર when we say lambda that is h by p, that is h upon mv. Now see, for photon we already discussed this thing, the momentum p that is h nu by c. So we can write, if we take this h by p on right hand side, then on left hand side we can write c by nu, but c by nu that is lambda. So here see, lambda that is h by p. So if we consider the photon, which one is with momentum p equal to h nu by c, then if we calculate its wavelength, then it also comes to lambda equal to h by p. Okay. Now see here, we already discussed this thing. When any electron is accelerated with the potential difference of v volt, the kinetic energy gained by it, that is given by ev. That is given by ev. But kinetic energy of the particle, as per definition, is given by half mv square. So we can write kinetic energy k, that is half mv square. Now suppose here we multiply and divide by mass m, then we can write m square v square by 2m, but m square v square, that is p square. So p square by 2m. So we can write the momentum p, that is equal to under root 2mk. Now we can replace this kinetic energy k, that is by ev. So we can write the equation of the momentum, that is under root 2mev. Now the Broglie wavelength, lambda that is h by p. So h, p is replaced by under root 2mk, or we can write h upon under root 2mev. Now see, h, 2me, all are constants. So here, if we substitute the values of h, m and e, and then after if we solve it, then we will get lambda that is 1.227 upon under root v nanometer. Now suppose here the value of v that we substitute equal to 120 volt, then this particular equation will give you the answer 0.112 nanometer. હવે આ જે આન્સર આવ્યો ને 0.112 nanometer, તો આ એપ્રોક્સિમેટલી જે એટમિક પ્લેન્સની અંદર એટમ્સની વચ્ચેનું જે સ્પેસિંગ હોય છે એના ઓર્ડરમાં આવે છે. એટલે એક આઈડિયા એ લોકોને એ આવ્યો કે with the help of diffraction experiments of electron and x-rays, કારણ કે x-rays ની wavelength પાછી આ ઓર્ડરની અંદર આવે છે, તો એનાથી આપણે આનું વેરિફિકેશન લઈ શકીએ. that is possible એમ, right? ચાલો, see, so the Broglie suggested this thing, the particle can behave as a wave, but it was just hypothesis. Okay, but calculation suggested this thing. Say, with the help of analogous with the X-ray diffraction of the crystal, one can verify this thing whether this happens or not. So scientists Davison and Germer performed one experiment related to this phenomenon. This one is the experimental arrangement in which the electron gun was taken and it was here connected with low tension potential difference. So with the help of this particular low tension potential difference, the cathode in the electron gun was heated, which emit the electrons. Here the cathode was coated with barium oxide, so it can emit the electrons at low tension. And then here the electron gun was connected with high tension, means high potential difference, and another cylinder was placed against it with two holes on the axis of it, so that when these electrons emitted from the electron gun enter to this particular cylinder, then due to this high tension potential difference will be accelerated, as well as the well confined collimated beam of the electron will be prepared. And then after that particular collimated electron beam was incidented on the nickel crystal, and then after the diffraction of it, or we can say scattering of it at different angles, was measured. So there was a movable detector, or we can say collector, which one was connected with galvanometer, and that particular detector can be moved on the circular scale. So when we place it at different positions, then with the help of the measurement of the current in the galvanometer, one can measure the intensity of the scattered electrons at different angles. This type of experiment was performed by Davison and Germer. This entire arrangement was placed in the evacuated chamber, right? So when the electrons are scattered, their interaction with any other particle not possible. Okay? See, then in this particular experiment, the observations were taken for different accelerating voltage starting from 44 volt to 68 volt. And for each accelerating voltage, they measured the intensity of the scattering beam at different angle. એટલે કે સપોઝ પહેલા આપણે 44 વોલ્ટ એક્સેલરેટિંગ વોલ્ટેજ રાખ્યા અને ઇલેક્ટ્રોન ને નિકલ ક્રિસ્ટલ ઉપર ઇન્સિડેન્ટ કર્યા, ત્યાંથી એ સ્કેટર્ડ થયા. હવે માનો કે આપણે ડિટેક્ટરને at the scattering angle 10 degree, scattering angle, that is the angle between the direction of the incident beam and the scattered beam. Okay, તો 10 ડિગ્રીએ આપણે રાખ્યું અને કરંટ મેઝર કર્યો, કારણ કે ઇલેક્ટ્રોન આવ્યા એને આપણે ડિટેક્ટરથી અથવા તો કલેક્ટરથી કલેક્ટ કરી અને ગેલ્વેનોમીટરમાંથી પાસ કર્યા, એટલે કરંટ મેઝર થશે. ઓકે, પછી આપણે એને મૂકીએ 20 ડિગ્રીએ, 30 ડિગ્રીએ, 40 ડિગ્રીએ, 50 ડિગ્રીએ, લાઈક ધેટ. પછી 44 ની જગ્યાએ આપણે 46 વોલ્ટ રાખીએ એક્સેલરેટિંગ વોલ્ટેજ, અને આખો એક્સપેરિમેન્ટ પછી રિપીટ કરીએ, લાઈક ધેટ. The observations were taken. Then see the important thing now in the result. It was noticed that a strong peak appear in the intensity of the scattered electron for an accelerating voltage of 54 volt at a scattering angle of 50 degree. Clear? Now see, now from the electron diffraction measurement, the wavelength measured for that diffracted beam, that was of the order of 0.165 nanometer. And now if we substitute the value of the voltage 54 volt in the equation of the Broglie wavelength lambda equal to h by p, later on we derived this one as 1.227 upon root v nanometer. So in this equation, if we substitute here v equal to 54, then your answer that will be very close to this 0.165 meter. So scattering of electron was exactly like the diffraction of X-rays. And then with the help of this experiment, it was confirmed, yes, particle have the wave nature. So in certain favorable conditions or circumstances, particle also behave as a wave. So then after the duality of wave and particle was established and all accepted this thing, in nature there is the duality. Clear?